We are moving forward to Juergen Schmidhuber, the person in the labs of which we see the foundation of the most popular neural networks. Now, Juergen is the head advisor to AIRI, and he's the head of the lab in the Institute of the Research in Dalemole AI. Our distinguished speaker is going to talk about the most cited neural networks of the 20th and the 21st century, how they operate and how they evolve.
Let me first thank the organizers for the invitation. This is my name and how to pronounce my name. I drew this cartoon of a self-reflecting robot in 2006. Modern artificial intelligence is dominated by artificial neural networks and deep learning. Today I'll speak about the 5 most frequently cited neural networks. I like speaking about them because all of them either stem from my labs in Munich and in Switzerland, or they are variants of methods developed in my labs. And here I'll discuss first the so-called long short-term memory, or LSTM, the most cited neural net of the 20th century. Second, the ResNet, the most frequently cited neural network of the 21st century, which is an open-gated version of our highway net, which was the first working really deep feed-forward network with hundreds of layers. Such deep neural nets are now widely used in thousands of applications. Third, I'll talk about AlexNet and VGGNet, the second and third most frequently cited neural nets of the 21st century, both building on our earlier DANnet, which in 2011 was the first deep convolutional neural net to achieve superhuman performance in a computer vision contest. DANnet actually had a monopoly on winning such contests. Fourth, generative adversarial networks are now widely used to invent realistically looking images and artworks. Such GANs are an instance of my adversarial artificial curiosity published in 1990, where 2 neural networks fight each other in a minimax game. And fifth, variants of so-called transformers, now widely used in natural language processing. Linear transformers are formally equivalent to the fast-weight programmers I published in 1991. In fact, most of this really started in our miraculous year of 1990 to 1991, when few people were interested because compute was 1,000,000 times more expensive than today. But today, billions of people are affected by this. Let me start with LSTM. It is a recurrent neural network, the most powerful type of neural net. It can, in principle, run any program that you can run on your laptop. It is a bit inspired by the human brain, which has roughly 100 billion little processors called neurons, each connected to 10,000 other neurons on average. Some of them are input neurons that feed the rest with real-valued numbers that represent data, such as video and audio. And others are output neurons that control muscles. Most neurons are hidden in between where thinking takes place. Recurrent connections allow for a memory of past events still circling around in the system. Each connection has a strength or a weight, which determines how strongly does this neuron over here influence that neuron over there. And your brain apparently learns by changing these connection strengths. Similar for our LSTM, which learns better than previous methods to recognize speech, or handwriting, or video, or to minimize pain and maximize pleasure, to drive cars and all kinds of other applications. According to Google Scholar, our 1997 journal publication on long short-term memory is now the most cited neural net paper of the 20th century. Here you see a single LSTM cell. Many such cells are connected in a big network which learns from training examples to improve some performance measure. And the net learns by gradient descent in weight space, by making some of the weights stronger and others weaker. And the red unit in the center is very simple but essential. It has a recurrent connection to itself with a weight of 1.0 that implements non-vanishing, non-exploding information flow. And it is surrounded by multiplicative gates which learn to control the flow. And that's the little secret that makes LSTM very deep, in the sense that it can learn to bridge very long time lags between relevant events in the input stream. LSTMs are now permeating the modern world with innumerable applications, including in healthcare, robotics, game playing, speech processing, machine translation, you name it. They are used billions of times a day by countless people. This led Bloomberg to say that LSTM is arguably the most commercial AI achievement. LSTMs, as we know them today, were made possible through my brilliant students, especially Sepp Hochreiter, who had essential insights already in his 1991 diploma thesis, Felix Geers, Alex Graves, Dan Wierstra, and others. For example, Dan Wierstra was the lead author of our papers from 2007 to 2010 on training LSTM without a teacher, no supervising teacher, through reinforcement learning to maximize rewards in an environment through something called policy gradients. In the 2010s, this became the method of choice for training reinforcement learning agents in complex environments, and impressive applications include DeepMind's StarCraft video game player and OpenAI's Dota video game player, and a dexterous robot hand that learned to do complicated things. And note that video games are much harder for AI than chess or Go. Bill Gates called this a huge milestone in advancing artificial intelligence. LSTM is also heavily used in healthcare. I made this drawing in 2020 at the beginning of the COVID crisis. LSTM was used for COVID-19 detection, COVID-19 classification, COVID-19 prediction, and so on. In fact, Google Scholar lists innumerable medical articles that have LSTM in their title. Here are some of them. For example, on diabetes, diagnosis of arrhythmia, protein secondary structure prediction, cardiovascular disease risk factors prediction, you name it. LSTM is also used in chemistry, drug design, analysis and prediction of water quality, air pollutant concentration estimation, and many other use cases. I like applications in chemistry. A neural net can learn from examples to become an artificial chemist and to model chemical reactions. Input ingredients plus conditions such as temperature, pressure, catalysts, etc. yield output molecules with certain properties. And then we work the trained neural networks backwards. So once they are good artificial chemists, we work them backwards. Now I say, I want to have a substance in the output that does this, that has such properties. Which ingredients do I need? And then we try the neural net suggestions in the real world, and this may save lots of time and physical resources in the design of new molecules. In fact, the jaws of chemical engineers dropped when they saw how well this can work. The most famous LSTM applications are probably those on your smartphone. Since 2015, LSTM, trained by our CTC Connections Temporal Classification of 2006. First author, my student Alex Graves, has done Google's greatly improved speech recognition on billions of smartphones. Our LSTM also was the core of the greatly improved Google Translate in 2016. In fact, by 2016, over a quarter of the awesome computational power for inference in all those Google data centers was used for LSTM. Facebook announced in 2017 that they are using LSTM to translate 30 billion messages per week, or over 50,000 per second. LSTM also learned to improve Microsoft's products and Apple's Siri and QuickType on a billion iPhones, and to create the answers of Amazon's Alexa. The great companies from Asia, Samsung, Alibaba, Tencent, Huawei, etc., are also using it a lot. So much about the most cited neural net of the 20th century. What's the most frequently cited neural net paper of the 21st century? It's the one by he and colleagues that introduced the name ResNet in December 2015. Of course, it cites our earlier highway net of May 2015, of which ResNet is a version. Let me say more about that. Deep learning is all about depth, about the number of layers in neural nets. Usually, deeper is better. Before 2015, however, feed-forward neural networks had at most a few tens of layers, maybe 20 or 30. Deeper nets did not work. But in May 2015, there was something new, a working, much deeper net with hundreds of layers. And that was our highway net, made possible through my brilliant students, Rupesh Kumar Srivastava and Klaus Greff. And like LSTM, the highway net implements non-vanishing, non-exploding, constant information flow in the system controlled by multiplicative gates. And that's what makes the feed-forward highway nets very deep in the sense of the deep recurrent LSTM. Half a year later, the instance of our highway net called ResNet won the 2015 ImageNet Challenge. And when comparing the two, ResNets are, in fact, highway nets whose multiplicative gates always remain open. Highway nets showed how very deep neural nets with skip connections work, and they perform roughly as well as ResNets on ImageNet. The US Patent Office granted a patent for this invention to our company Nisense in 2021. That is, the most frequently cited neural nets of the 20th and 21st century are closely connected, because the highway net is actually the feed-forward neural net version of our recurrent LSTM. As I said, deep learning is all about neural net depth, and LSTMs brought essentially unlimited depth to supervised recurrent neural networks with recurrent connections, and highway nets brought it to feed-forward neural networks where you don't have cycles within the network. The second most frequently cited neural net paper of the 21st century describes the AlexNet by Krzyzewski and colleagues in 2012, which is a convolutional neural net, CNN, on graphics processing units, on GPU, which makes it fast. And it's similar to our earlier DANet of 2011, which had a temporary monopoly on winning computer vision contests. And it won 4 of them before AlexNet arrived on the scene. AlexNet also used rectified linear units as proposed by von der Malsburg in 1973, and it used dropout or actually the stochastic delta rule as proposed by Hansen in 1990. And the 21st century's third most frequently cited neural net, the VGG network by Simonian and Zisserman in 2014, is also similar to the DANet of 2011, using its trick of increasing neural network depth through small convolutional filters. That may say something to you if you already know something about CNN. DANet was made possible through my postdoc, Dan Juergen from Romania, with the help of Uli Meyer and Jonathan Mashi. Of course, we did not invent CNNs. The basic deep convolutional neural network architecture with alternating convolutional layers and downsampling layers was already described by Kunihiko Fukushima in 1979. Neural nets with convolutions were then combined about 8 years later in 1987 with weight sharing and gradient descent through backpropagation by Alex Weibel, also in Japan. Modern backpropagation, or the reverse mode of automatic differentiation in sparse, discrete neural network-like nets was already old by then. It was first described by Seppo Linnainmaa in Finland in 1970 in a master's thesis. Even before that, deep learning started in the Ukraine, back then the USSR, through Alexei Grigorovich Ivaknenko and Valentin Lapa in 1965. And they really pioneered deep learning in feed-forward networks that learn internal representations. They didn't have any limit on the number of layers in their systems, and they had already nets with 8 layers in 1970. So Ivaknenko and Lapa went substantially beyond the shallow learning by Gauss and Legendre around 1800. Gauss and Legendre, they used linear regression and the method of least squares to model the training data, and we are still doing that today. So our DANet wasn't really new, except that it made such neural networks, such convolutional neural networks, very fast on GPU. And that was the new thing. In 2011 and 2012, that was good enough to win every computer vision contest it entered, and 4 of them in a row: Chinese handwriting, traffic signs for self-driving cars, brain image segmentation, and medical imaging for cancer detection, all before AlexNet and VGGNet. Remarkably, already in 2011, DANet achieved the first superhuman performance in a computer vision challenge, although back then compute was still 100 times more expensive than today. So today we can do 100 times more for the same price. Here, DANet was actually 3 times better than the runner-up, which was the net by Dr. LeCun's team. In September 2012, DANet was also the first deep CNN to win a contest in medical imaging. This was about breast cancer detection, and our CNN image scanners were 1,000 times faster than previous methods. And the significance of these kinds of improvements for the healthcare industry is obvious. Today, IBM and Siemens and many startups are pursuing this approach. Note also that healthcare by itself is about 10% of the world's GDP. Now, it's great to see that our research is really improving healthcare and saving human lives. DANet, and therefore also AlexNet and VGGNet, actually followed our earlier breakthrough of 2010, also through Dan Juergen, for purely supervised deep neural nets. In fact, before 2010, many AI people thought you need unsupervised pre-training to train deep neural networks, and such deep neural nets based on unsupervised pre-training were actually introduced by myself in 1991 and later championed by an AlexNet co-author smarter. But by 2010, our purely supervised, recurrent, and feed-forward neural networks outperformed all other methods on famous benchmark problems. And in the 2010s, this little supervised learning revolution quickly spread from Europe to other continents. Another highly cited neural net paper of 2014 on generative adversarial networks, or GANs, describes a system that's now widely used to invent realistically looking images and artworks, like the one shown here, made by a so-called style GAN. This image looks like the portrait of a woman, but it was invented by a style GAN. And in fact, GANs and style GANs are an application of my popular principle of adversarial artificial curiosity from 1990, where two dueling neural networks fight each other, maximizing each other's loss in a minimax game. How does that work? The first net probabilistically generates outputs that may influence an environment. The second net sees the outputs of the first guy and predicts the environmental reactions to the outputs of this first net. And so using gradient descent or backpropagation, the second net minimizes its error, thus becoming a better predictor. But in a zero-sum game, the reward-maximizing first net tries to find sequences of outputs that maximize the error of the second net. So the first net's loss is the second net's gain. So the first net likes to create situations where the second net is still surprised and can still learn something. That's what I called artificial curiosity in 1990. And GANs and style GANs are an instance of this, where the trials are constrained such that they remain very short, just one shot, just one action and one environmental reaction, like in so-called bandit problems. Note that such artificial curiosity and creativity has become really important. We do not only have AIs that slavishly imitate human teachers or pursue human-given goals. No, since 1990, we really have neural systems that set themselves their own goals, that ask their own questions, that invent their own experiments to figure out how the world works, like babies and scientists do. Finally, recently, transformers named by Vaswani et al. In 2017, have been all the rage. For example, in OpenAI's GPT-3, they have learned to generate human-sounding text. It turns out that transformers are an extension of the fast-weight programmers of 1991, which I published 30 years ago, which amount to being what's now called linear transformers, apart from normalization. For the cognoscenti, the so-called self-attention in standard transformers combines this with a projection and softmax, using attention terminology like the one I used in 1993. So back then, I didn't have the softmax, which is important. How do those fast-weight programmers work? A feed-forward net slowly learns by gradient descent to program changes of fast weights of another net. In the image to the left, there's a separate output unit of the slow net for each connection of the fast net. While processing a data sequence, the slow net can quickly reprogram the transformation or the mapping from inputs to outputs implemented by the fast net. That is, at one time, the fastnet might process a certain input pattern in the input stream in a certain way, and later it might process the same input in a different way, because the slow network has reprogrammed it in the meantime. So that's how the fastnet can implement a memory of the past, like an LSTM, although neither the slownet nor the fastnet have recurrent connections. In the image to the right, the slow net computes fast weight changes through additive outer products of self-invented activation patterns, now often called keys and values for self-attention. So the slow net says, in the future, the fast net should associate this key with this value, this key with this value, and the fast net quickly changes to obey this command. And over time, the slow net learns to come up with good keys and values at the right time. So in a way, it learns a bit how to think. I believe this concept of fast-weight programmers is still very important. It goes beyond standard transformers. Very recently, my team has created fast-weight programmers where both the slow and the fast net are recurrent, so they aren't feed-forward any longer, and where the slow net programs the fast net through self-invented learning rates, through sequences of programming instructions that are actually like the well-known delta rules. And in our experiments, these fast-weight programmers were better able to generalize in a systematic way than previous methods. There are upcoming NeurIPS papers on fast-weight programmers with Kazuki IRI, Emanuel Schlag, Robert Jordash, and Luis Kirsch in my lab. All of that is easy to find on Axif. You see that much of what I told you today has its roots in our miraculous year 1990-91 at Tech University Munich, the first very deep learning in artificial neural networks through unsupervised pre-training, then generative adversarial networks and artificial curiosity for agents that invent their own problems, then vanishing gradients, and as a consequence, long short-term memory, or LSTM, now in your pockets on your smartphones. The learning of sequential neural attention, planning with recurrent models of the world, distilling a teacher neural network into a student neural network, fast-weight programmers that I just mentioned, today called linear transformers, and other exciting stuff. In the 2010s, all of this work was feverishly built on by an outstanding community of machine learning researchers, engineers, and practitioners to create amazing things that have impacted the lives of billions of people worldwide. I mentioned citations, but I have a disclaimer. Of course, citation counts are poor indicators of truly pioneering work. As I pointed out in the journal Nature in 2011, where I wrote, like the less than worthless collateralized debt obligations, the CDOs that drove the 2008 financial bubble, citations are easy to print and inflate, providing an incentive for professors to maximize citation counts instead of scientific progress, which is the thing they should maximize. Witness how relatively unknown scientists can now collect more citations than the most influential founders of their fields. In the 2010s, we founded our company Nascence. It is pronounced like nascence, like birth in English, but it's spelled in a different way because it's about the birth of a general purpose neural network-based artificial intelligence. It's about the big thing of the future, AI in the physical world for robots and industrial processes, etc. Today, most profits in AI are in the virtual world for marketing and selling ads. That's what the big platform companies on the Pacific Rim do: Alibaba, Amazon, Facebook, Tencent, Google, Baidu. But marketing is just a tiny fraction of the world economy. And the much bigger part is the rest, which is going to be invaded by AI as well, like in the movies. Now, Nascence is creating what we call deep digital twins of industrial processes, and it's using these deep digital twins, deep networks that model these processes, to improve the control of these industrial processes. Our motto has been AI for all. It's all about making human lives longer and easier and healthier. Finally, let me put all of this into historic context. By historic context, I mean the time since the Big Bang, which happened 13.8 billion years ago. Let's divide this time by 1,000. And we come out about 13.5 million years ago when something very important happened. The first hominids emerged, our ancestors. And almost everything we consider important occurred in those past 13.5 million years. Let's divide this time again by 1,000, and we come out about 13,000 years ago when something very important happened, the Neolithic Revolution, when agriculture was invented, animals were domesticated, and civilization was born in the first settlements. And almost everything we consider important occurred in those past 13,000 years. Now we see that all of civilization is just a flash in world history, just 1/1,000,000th of the time since the Big Bang. And the first farmer lived almost at the same time as the first cosmonaut and the first computer scientist. And now, in the very near future, at most a few decades from now, there will be for the first time little cheap machines that can compute as much as a human brain, because every 5 years, compute is getting 10 times cheaper, a trend that has held since 1941, when Konrad Zuse built the first working program-controlled general-purpose computer. And if the trend does not break, a few decades later, there will be little cheap devices that can compute as much as all 10 billion human brains taken together. And there will be billions of such devices. Almost all of intelligence will be non-human. Everything will change. Maybe then we will have to divide the last time interval again by 1,000, and only 13 years later they will say almost everything we consider important happened in those past 13 years. But time will not stop then. What will curious meta-learning AIs that invent their own goals, which have existed in my lab for decades, what will they do? Of course, most of them will go where the physical resources are to make more and bigger and better AIs. So they will have to leave the Earth. And within a few tens of billions of years, only limited by the speed limits, by light speed, within a few tens of billions of years, they will colonize and transform the entire visible universe. And those who don't want to take part in this, they won't have an impact. And there's plenty of time because the universe is still young, only 13.8 billion years old. Remember, when we kept dividing by 1,000, now let's multiply by 1,000. Let's look ahead to a time when the cosmos will be 1,000 times older than it is now. By then, it will be permeated and totally shaped by intelligence. As I have said many times before, this is more than just another industrial revolution. This is something new that transcends humankind and even biology, and it is a privilege to witness its beginnings and to contribute something to it. Thank you for your patience.
Mr. Schmidhuber, hello. Thank you for joining us. It was a great report and it was of great interest. I would like to ask you some questions that are coming right now from our viewers. Would you be so kind to answer them? I'm sorry?
I would love to.
Okay. So can you name the most promising directions in the development of AI in the nearest future? What, in your opinion, should be the focus of research?
I personally think that systems that learn to think in an abstract way are going to be very important. And if you look at recent publications in my lab, you will see there's a lot about this, where you have a thinking machine that learns to reprogram its internal space in a way that is good for solving a particular problem. And as it is trying to solve problems, it's evaluating the different options of going forward. Basically, it's learning to plan what's going to happen in the future if I do that and that. But instead of planning in a millisecond by millisecond pixel-based fashion, as we had in the 1990s, around 1990, they are thinking in a high-level fashion. For example, suppose you want to go from Moscow to Beijing. You are not planning this trip by planning every little movement of your fingers. No, you are just thinking of, okay, first I have to go to the taxi station, then I take a cab to the Moscow airport, then I enter the plane, and for 9 hours nothing is happening, and so on. And so in these very compact, abstract ways, that's how humans think about the future, and selectively, efficiently, without using too many thinking resources, they learn to plan efficiently and to minimize their limited resources. And this is something where we are getting much closer to, and the keywords there are meta-learning and abstractions and fast-way programmers that learn to reprogram parts of their internal space by thinking about it.
Okay, but most scientists proclaim that the peculiarity of human thinking, human brain, is the ability to resolve problem in a creative manner. So in your opinion, in your point of view, will AI be able to create something truly new?
Well, computer science in general and AI in particular has created many truly new things in the past. Obviously, already in 1997, when for the first time a machine was the best chess player in the world, it came up with certain sequences of moves that were not in the repertoire of any human. So even back then, this rather simple computer program already created something that humans didn't know. So in that sense, it's old news that computers can be creative, because they have created lots of stuff that humans could not create. And in recent years, this has accelerated because we have more computing power. So absolutely, maybe the question is, can computers not only create solutions to problems posed by people, so basically following the commands of humans, or can they also invent their own problems, like little babies do? Most of the time, babies are not, or kids are not trying to obey commands from their parents. No, they invent their own little experiments. They figure out how the world works by playing with the toys. They learn how does the input video change if you rotate this little toy, and that's how they learn about physics and about 3D and so on. And they set themselves their own goals all the time. Just like scientists are setting themselves their own goals all the time. And as babies get older and maybe become scientists, it's just that the experiments are getting more expensive, because at some point then the experiment maybe involves a $5 billion particle accelerator in CERN in Switzerland or another place to find the Higgs boson, stuff like that. However, it's already now the case that we have systems that generate their own goals and pursue then plans for satisfying these goals, and the whole thing is quite detached from human influence. So both these types of applied creativity to human-given problems and pure creativity, where the problems themselves are invented by the AIs, both of these things already exist in present AIs, and it's just going to become bigger, and it's going to scale.
Thank you very much. Thank you very much for your opinion and for your report. Thank you once again, and bye-bye. It was nice. It was a pleasure.
Thank you. It was my pleasure. Thank you.
Bye-bye.